Hello, this is Dr. Cole Woolley, and this lesson is called Understanding Optical Rotation. I'm going to use a different analytical test to be able to help me differentiate between Oman frankincense and Somalia frankincense. Let's look at optical rotation. First of all, optical rotation is based on the fact that many of the components of frankincense essential oil have a left-hand version and a right-hand version. This is called handedness. The molecules are called chiral, and this is chirality. So there's left-hand molecules and right-hand molecules. Now this is very important because if I try to take both of my hands and put them on top of each other, they don't match up. They're non-superimposable. They are mirror images of each other, and that's an identification of chiral molecules. Let's look at a couple of examples. Here's alpha-pinene. Imagine the mirror being the dotted line in the middle. If you look at the structure of each of these left and right-hand molecules, they will show you that they are mirror images. They're non-superimposable. They are distinct. They share a lot of properties, but they are distinctly different. Here's an example of the chirality or handedness of limonene. There's not just one limonene molecule, there are two limonene molecules. A left and a right-hand version. They are mirror images of each other. Here's an example of another common molecule in frankincense essential oil called saponine. Again, you see the right and left-hand molecules. They are mirror images of each other. There's not one saponine molecule. There are two saponine molecules. Now, it's very important that you understand that there's a way to differentiate between these two chiral molecules. For this, we need a light that passes through the sample. The arrow to the bottom represents the light. It's a polarized light. And as it passes through the sample, the polarized light goes through the left-hand molecule and shifts the light to the left. The polarized light going through the right-hand molecule will shift the light to the right. This difference in shifting the polarized light to the left or the right can help me figure out the difference between Somalia frankincense and Oman frankincense. This device is the polarimeter. It is used to determine the optical rotation of an essential oil, whether it's left-hand or right-hand dominant. The polarimeter is a very important analytical laboratory tool found in research and quality labs in essential oil companies. As a beam of light enters the polarimeter, it is separated into a polarized light, like a plane of light. And then it passes through the essential oil. When it passes through the essential oil, it twists either to the left or to the right. In this case, if limonene is L-limonene or minus limonene is in the polarimeter, it rotates the polarized light counterclockwise. This shows the angle that the polarized light was shifted. Now let's look at some essential oils and the different optical rotations determined from a polarimeter. Let's look at the ones that have a positive rotation from center. Orange oil and tangerine oil. Look how far the polarized light is moved to the right. Plus 94 degrees to plus 99 degrees for orange. For cedarwood, plus 65 degrees to plus 90 degrees. And if we go down to the bottom, we see cinnamon bark. Well, it's either minus 2 degrees or plus 2 degrees. Not very much of a change from the center. Now this happens because in orange oil, we mostly have limonene as a major component. And of that, those two components of limonene, the most abundant one is the plus limonene. So when the polarized light hits that, then it produces a big shift to the right. And when it goes to the minus limonene, it produces a small shift to the left. And when you add those two together, it's predominantly a big shift to the right. And so we have plus 94 degrees all the way up to plus 99 degrees. That's how polarized light can help us differentiate between orange oil and, let's say, lemon oil. Now let's look at the other half, the negative side of the optical rotation spectrum. First of all, we have lemongrass that has optical rotation of -3 all the way to +1. It's kind of like cinnamon bark. Juniper berry, -15 to 0 degrees. We also have peppermint, -24 degrees to -17 degrees. And down at the bottom, we have patchouli essential oil from -66 degrees all the way to -40 degrees. You can see that the polarimeter can help us determine the optical rotation and differentiate between essential oils. In this case, peppermint oil, the polarized light enters the minus menthol, which predominates in peppermint essential oil, and produces this huge shift to the left, where 99.9% of it is minus menthol. Whereas the plus menthol is only in there at about 0.1%, and so when polarized light hits that, it produces a very small shift to the right. So you put those two shifts together and it's predominantly to the left. And so you have -24 degrees to -17 degrees as the range for peppermint essential oil optical rotation. So this lesson has been all about understanding how optical rotation helps me as an analytical chemist differentiate between essential oils, sometimes that are very similar, like orange and tangerine, or possibly frankincense from Oman and frankincense from Somalia. That's part of the continual story. Optical rotation is basically the sum of the left and right-hand molecules that are found in the essential oils. Remember, there's 2 alpha-pinene, there's 2 limonene, there's 2 saponines, there's 2 beta-pinene. These chiral molecules are what make up essential oils. And in this case, frankincense essential oil, which is predominantly alpha-pinene, optical rotation might help us a lot.